excuse me, there are a number of ways to set up the determinant of a 3 by 3 matrix, but the definition is going to be this. Okay, you see that I've circled the number 2 in the first row in purple, the number 4 in green, and the number -1 in blue. Now, I start by writing down the first number, 2. And I multiply 2 then by the determinant of the matrix that has rows 1, 2, 3, 4. Those happen to be the same as the rows of this matrix here. And I did that kind of intentionally, but otherwise this thing is not related to this matrix, so you can kind of forget that. How did I get 1, 2, rows 1, 2, 3, 4 out of this matrix? Centered on the fact that I chose the number 2 here. Well, somebody saw it in class, first person that saw it said, well, you just take the row below the 2 and the column across from 2 and eliminate them, and that's the matrix you're left with, and that's absolutely correct. Okay? Now, next we go to the 4. We write down the 4, but we also write down a minus sign. Okay? We didn't write down a minus sign here. We wrote down a minus sign here. And we'll see what the pattern is. And the pattern's going to be just that, you know, every other number we're going to write down a minus sign. Now, if we choose the first row, that's going to work. And we could actually do the same thing with the first column, and the same rule would work. If we start with some other row or column, and we can do that, we've got to be a little more careful about whether we start with a positive or a negative. For right now, let's just talk about what happens when you do the first row, because that's easy enough to understand. Okay, so we put the negative in front of the 4, then we throw out the column, and we throw out the row. Let's see if there's any way for me to cover up the row and the column. I kind of got it. Leaving me the -2, the 1, the -2, and the 4. And that's what I have here. Okay? And then I do the -1. I'm back to positive. This one is positive. This one was a positive in front of whatever number I've got here, a negative in front of whatever number I've got here, and then the next one's going to be plus whatever number I've got there. And I throw out the row and the column. It's getting more difficult to do that. And I'm left with the 2, the 1, and the 3, -2 and the 1, and the 1 and the 3 for my rows. Okay, that's it. I'm done. I finished my first row. And now all I've got to do is calculate these 2 by 2 determinants, which are all easy. This one, as we already calculated, is -2. This one, -8 minus 2 gives me -10. -6 plus -1 gives me -7. Multiply these out, add them up, I get 43. Okay, very simple. Now it takes a little practice, but after you've done it a few times, there's nothing to it. And you've got to keep track of a lot of numbers, and might be a little bit error prone, but it's not that bad. Okay, well, let's do the same thing for this 4 by 4 matrix. What we do is no different. We start with the first number in the first row, which is 5, and then we do the determinant, what's left, when we throw out the first row and the first column. That leaves us this matrix, which I've written down here. Okay, then we go to the next number. We do minus this number, so I'll put a minus, and then in parentheses I've got my -2, and I've got that circled in red to match it up with this one. Okay, and then I throw out that column and that row, and I'm left, and you can verify it, with this determinant. Then I go to the next number, and it's going to be plus that number times the determinant I get when I throw out the column and the row. And I think I might have been saying row when I meant column, but you understand what I mean. And I get this. And then I take the 6, throw out the column and the row, and I get the matrix that you see here in the first 3 columns, ignoring the last. I can't really move my hand around that. And I get the determinant of this, and I've got to go to a minus in front of that 6. Okay, so I don't have a minus, I do. I don't have a minus, I do. Now when I say a minus, I mean a minus in front of whatever number this is. Obviously I have a minus from the -2, but I have a minus that. Then I have a plus the minus 3, and a minus the 6, plus the 5, minus the negative 2, plus the negative 3, minus the 6. Okay, well, you notice I haven't actually calculated the number here. And I really don't want to calculate the number because it's going to take a while. And in this case, there might be an easier way to calculate the determinant. And I'll allude to that in a minute. But if we're going by this rule, you see that now I've got 4 3x3 matrices. What am I going to do? I've got to evaluate each of these 3x3 matrices, and each one of these is evaluated by the same kind of procedure I did up here. Well, it doesn't take all that long to do this. You just got to write things down carefully in 10 minutes, and much shorter than that if you work fast. You could get this all evaluated. It's just that you got to realize that when you evaluate a 3x3 in general, you're going to have 3 2x2 matrices to evaluate and multiply by each of those by a number. So that's going to give you 3 2x2 matrices here, 3 here, 3 here, 3 here. That's 12 2x2 matrices. So it's not out of hand, but it's going to get there pretty quick if you keep making these matrices bigger. You got 12 2x2 matrices. If you had a 5x5 matrix, if you understand, you got 5 numbers in the first row, and when you throw out a row and a column, you're left with a 4x4 matrix. So you're going to have 5 4x4 matrices if you had a 5x5 to start with. And each 4x4 is going to give you 62 by 2s. It's going to give you 12 2x2s, so you're going to end up with 5 times 12, or 60 2x2 matrices. Even that is manageable. If you'd never get the arithmetic right, or you'd never be confident that you got the arithmetic right if you're writing it by hand. But it could be done. And it could be done in a reasonable time, 15-20 minutes. By the time you get up to a 10 by 10 matrix, you'd reduce that to 10 9 by 9 matrices, each of which would reduce to 9 8 by 8 matrices. Okay, so you'd have 9 times 8, or 72 8 by 8 matrices. And each of those would reduce to 7 by 7, so you'd have, actually you'd have 90, 10 9 by 9s, each 9 by 9 being 8 8 by 8s. Okay, so you'd have 90 8 by 8s, and then you'd have 90 times 70, 630, 7 by 7s. By the time you got down to the 2 by 2s, you'd have over 1 million matrices. 1 million 2 by 2s. Now the 2 by 2s are easy, but nobody is going to sit there and write it all out till they get 1 million, approximately 24,000 2 by 2s. Okay? Just a little over 1 million. Yeah, just a little over 1 million, so go ahead and do it. But, nobody's going to do that. Fortunately, there's an easier way. And the easier way that I'll just talk about right now, but we're going to see it. Okay, it'd take you a lifetime, well, maybe not that long, but to get that 1 million 2 by 2s, write them all down and all the matrices in between, take you quite a while, years. And if you're slow, you might not get it done in a lifetime. And I joked in class, somebody might do this. They might spend a lifetime doing this 10 by 10 matrix, and then, what would they put on their tombstone? They'd chisel in the 10 by 10 matrix equals whatever they got. And then somebody come along and look at it and do it in their head and say, yeah, he was off by a factor 2. No, you don't want to go there. Okay, ironic summary to a person's life work. Okay. What you would actually do with a 10 by 10 that's a lot more feasible is you can row reduce a 10 by 10 matrix. Now you really don't want to do that either, but it wouldn't take you a lifetime. You could probably do it in an hour, and then probably another hour to check it and find out you did it wrong, and then another day or two to figure out what you did wrong and finally get it right. But still, it could be done in an imaginable amount of time rather than reducing down to 1 million 2 by 2 matrices. So in the process of reducing that matrix, you write down exactly what your row operations were. Okay? And you know that if your row operation is to multiply a row by a number, that's going to multiply the determinant by that number. Okay, so if every number you multiplied by a row, you multiply out those numbers and you do the determinant of the reduced matrix. And of course, the determinant of the reduced matrix, if you reduce it all the way, is just 1. Either that or it can't be reduced all the way, and the determinant is 0. That's not difficult to find. Okay, so I'm just going to give you an overview where we can go instead of evaluating huge determinants. And then if you happen to interchange two rows in the process, well, you're going to have to write down a -1. So you're going to have to write down all the numbers you multiply by rows. Write down -1 every time you interchange two rows. Okay? And then if you add a multiple of a row to another, you don't have to write down anything because that doesn't change the determinant. You reduce the determinant down and you take the reduced determinant, and really you only need to reduce it to upper triangular form. And of course, if you get upper triangular form, you can reduce it to lower triangular form, and then the first row would only have a 1 and a bunch of zeros, and the first row of each matrix that you would end up with that you didn't multiply by 0 would just have a 1 in front of it. Well, you'd have to do that to see all that, but what I'm saying is really kind of simple. And that's how you would go about calculating the determinant of a 10 by 10 matrix. And if you can do all your arithmetic right, you can do that in less than an hour. Okay. Anyhow, there's kind of an introduction to determinants, and we'll go on here in just a minute.